In this video, we're going to start talking about the thermochemistry, and in this particular part, we're going to be talking about the internal energy and the first law of thermodynamics. So, to define an energy, energy is actually going to give you the capacity to do work. You may have heard people saying that, oh, I don't have any capacity to do work, which technically really means I don't really have any energy to do anything. Now, in physics, the mechanical energy is consisted of two parts. We have the kinetic energy and we have the potential energy. The kinetic energy comes from the motion. What that really means, if something is moving, it will have kinetic energy. For example, moving cars, moving train, moving plane, they all have the kinetic energy. However, the potential energy comes from the position with respect to the ground. If something is at a certain height, it's going to have a potential energy. So those roller coasters over at Six Flags is when they go on to a certain height, they acquires the potential energy. So that's going to be the sum of the kinetic energy and the potential energy in a system is equal to the mechanical energy, and it's also equal to the total internal energy. But obviously in chemistry, we don't really have a kinetic energy and the potential energy, but we have something similar to those. We have thermal energy that actually comes from the temperature. So if there isn't a change in the temperature, you can figure out what the thermal energy is going to be for that particular reaction by calculating the change in temperature. And then chemical energy obviously comes from the chemical bonds. If you're breaking a bond, you're making a bond, there is going to be either a release or a gain of the energy. And you can also say the chemical energy also pertains to the position of the valence electrons. So those are the two types of energies that we're going to be focusing on in thermochemistry. Okay, well, let's talk about the first law of thermodynamics, which is also called the laws of conservation of energy. And you may have heard this before. Uh, the total energy of the universe is constant. So that's what this first law of thermodynamics says. What that really means, I cannot create an energy and I cannot destroy an energy. And you can transform one form of the energy to another form. And in a typical roller coaster example, you convert the kinetic energy into potential energy and vice versa. So you're not really destroying the total energy, but you're just changing it from one form to another form. And that applies in chemical reactions as well. We're not going to be creating new energy. It's just going to be the energy stored in the bonds, and then when we either make those or break those, there is going to be either a release or gain of energy based on that. Okay, well, energy is actually a state function, and it's important to understand what that really means. The state function depends on the initial and the final values, and it's independent of the path that it takes to reach the final position. Suppose I have this mountain here. It doesn't really look like a mountain, but suppose this is a mountain. And there's two ways to go from point A to point B. If it's me, I'll probably take this path right there. I'll go all the way to the end here, and then I'll probably start climbing up onto the mountain to get to point B. But then if there is someone else, maybe a rock climber, then he may just go up here straight to the point B. Now, how much energy that will be taken here is just going to be dependent on the initial and the final position. So your total energy here, I will say the change in energy is going to be the energy at the final position, which is at B, minus the energy at the initial position. And then you look at the shortest distance in between. So it doesn't matter if you follow this pink road or if you follow this yellow road, the total change in energy is going to be the same regardless. So that's what the state function is. Your internal energy is the state function, and the other examples of state function is going to be the work is a state function, as long as there is no non-conservative work done being involved. The delta H is a state function, the delta G is a state function, so all those guys are going to be the state functions, which means they depend only on the initial and the final values. Okay, well, let's talk about the exchange of the energy between the system and the surroundings. There is a very clear definition of the system and the surroundings. And I don't want to really write it out. I'll just kind of explain what that really means. A system is anything that you're kind of studying on. Let's suppose you are talking about the planet Earth. And if you're studying the planet Earth, everything else outside the planet Earth becomes your surroundings. So your Earth is going to be the system in that case. Other planets in this galaxy or in our galaxy is going to be the surrounding in that case. Let's say you're talking about maybe United States, and if you're studying the United States, maybe the environmental studies or anything on that, then your United States becomes the system, and the other part of the world becomes the surrounding. So that's how you really look at. If you do a reaction in a container, then your container becomes the system, and anything outside the surroundings is going to be your uh, your surroundings. Okay, well, there's two things that can happen. Either the system can lose energy, so if there is an energy flow going from the system to the surroundings like this, then the system is said to be losing the energy, and in that case, the change in delta E is going to be less than zero, or another way of saying it's going to have a negative change in energy. Okay, and the other possibility would be what if the system is actually gaining energy from the surroundings. So if the energy flow comes from the surroundings to the systems like this, then systems set to have gained energy, total internal energy, and in that case the delta E is actually going to be bigger than zero, and that would be said to be positive. Okay, that's gonna have how you're gonna be reading the energy flow from the systems to the surroundings and the vice versa. There are different types of system, and sometimes the teacher asks you questions just on the system, so make sure you are aware of the different types of systems. Uh, the first one is going to be called an open system, and an open system is like an open container that contains water or maybe some sort of liquid. So over time, let's suppose I have this glass water here. If I leave this open and outside, two things can happen. It will either gain the temperature or gain the energy or lose the energy depending on what temperature you have outside. But then over time it will also lose some of the water because it's going to start evaporating. So there is an exchange of the energy and the matter. So that's called an open system. However, a typical example of an enclosed system would be a coffee cup. And make sure you have a lid on it. So when you have a lid on it, this coffee cup doesn't really stay hot for a long time. It may keep the coffee hot for a little bit, but then over time it's going to start losing energy and your coffee is going to get cooler. So when the coffee gets cooler, but you don't really lose the coffee because it's covered by the lid. So in that case, there is an exchange of the energy only. You don't really lose the matter. Okay, so that's your closed system. And then you could also have the isolated system, and obviously it's very hard to get an isolated system in our life. You could, however, buy something really expensive that are totally isolated, where there is no exchange of the matter and the energy. And a lot of chemical reactions are actually done in isolated systems to figure out how much energy a particular reaction produces. A good example is like a bomb calorimetry, and a bomb calorimetry is used to figure out how much energy a particular food is going to produce. So in that case, you have to make sure it doesn't lose energy to the surroundings. So in those cases, you use a very isolated system. So in that, there is no energy and matter exchange. So those are your three different types of systems. Make sure you know those. Okay, so then let's talk about the equation of the first law of thermodynamics. The equation of the first law of thermodynamics have the internal energy, that's going to be the delta E, and it's got the Q, which is going to be the heat. And obviously the heat could be going into the system or coming out of the system. I will talk about that in a minute. And the work done, the W stands for the work done, and that work could be done on the system or by the system. Okay, so Depending on how the energy flows are, like whether the work is done on the system, by the system, or the heat goes into the system or out of the system, you have to take those signs accordingly. Okay, so make sure you guys are memorize what the sign convention gonna be for this Q, W, and delta E. So if, let's say the Q is your heat, if system gains the thermal energy, so another way of saying the system gets warmed up in a bit, then you are putting in the energy into the system. In that case, the Q is going to be taken as positive. Okay. If system loses the thermal energy, another way of saying system gets cooler, then it's going to be a negative sign. Okay, so then a lot of times the question does actually tell you whether the heat is being put into the system or out of the system. Okay, so then the work done, if the work is done on the system, it's going to be taken as positive. That's one way of saying. The other way of saying the same thing would be the work done by the surroundings. So if the surroundings are doing the work, where are they doing the work on? Well, they're doing the work on the system. All right, so make sure you are familiar with the terminology here. If the work is done by the system, then it's going to be taken as negative. If the work is done by the system, where this system doing the work? Well, it's doing the work on the surroundings. So it's the same as saying this work is done on the surroundings, and that's going to be a negative sign as well. Okay, and then obviously using the values of Q and W, sometimes you'll have both and sometimes you'll have only one, and we'll talk about that a little bit. And once you use those values, you can figure out what the delta E going to be using this equation that we just have on the top here. And if your energy flows into the system, then your change in energy is going to be obviously positive, because the system is gaining the total internal energy in that case. And if your total energy flows out of the system, then you losing the energy into the surroundings, and your delta E is actually going to be a negative sign. Okay, well, make sure you are familiar with this sign convention, and let's talk about a question that actually relates to these sign conventions. Okay, so let's say we have calculate the total energy of total change in the internal energy, so delta E, of a system when 400 joules of heat is added. Okay, so make sure you are paying close attention to how the question is worded here. So 400 joules of heat is added to expand O2. So that means you're actually adding that much heat into the system. So your Q is going to be positive 400 joules. Okay, and then gas does 300 joules of the work on its surroundings. So when it says the work is done on the surroundings, that means the work is done by the system. So since it's done by the system, it's going to be negative 350 joules. Okay, and then we do know the formula, the delta E, is actually going to be equal to Q plus W, and our Q is going to be 400 joules, and then plus your W is going to be minus 350 joules. Okay, and since you have both of those, then all you really got to do is just do the math here, and it's going to come out to be 50 joules overall, and that's going to be a positive. So what does that mean? The internal energy is positive. That means system is gaining the energy. So system gaining the total internal energy. All right, so sometime you could see something like a very simple question that's just going to be based on this first law of thermodynamic equation, and the most difficult part in that is just going to be figuring out the signs. So once you figure out the signs, it's all about just plugging in those values and defining your answer. So that was the first law of thermodynamics and the internal energy. In the next tutorial, we're going to be talking about how you're going to be actually quantitatively calculating this Q and W. All right, so if you have any questions, leave the comments in the section below.